Today we're going to talk about quarks, leptons, and antiparticles. So hopefully you recall from the last video, there were two types of fundamental particle that made up all of matter. There were the quarks and there were the leptons. And when I'm talking about matter here, I'm primarily talking about protons, neutrons, and electrons. And electrons are part of the group of leptons. With the quarks, there's actually two ways that they form. They form into pairs, really a particle-antiparticle pair, and those ones are called mesons. And they form into triplets, groups of 3 quarks, and these ones are called baryons. And it's within this group of baryons that you find the neutrons and the protons. Now it turns out there's all different kinds of mesons and all different kinds of baryons. They're not nearly as common as neutrons and protons because they have very, very short lifetimes. They're unstable particles. However, the only way that physicists have been able to explain all the different mesons and baryons that they've observed in particle detectors is by assuming that there's 6 different types of quark. But depending on how you define it, you could say that there's 12 types or even 36 types of quark. Let's stick with the 6 for now. So you'll notice that we kind of have pairs here. We have an up quark and a down quark, and another pair of a charm quark and a strange quark, and then the third pair being a top quark and a bottom quark. And what you want to notice here is that in each one of the pairs, one has charge plus 2/3, and the other has a charge of negative 1/3. So let's see if we can use charge to determine a very common baryon that consists of 2 up quarks and a down quark. Pause the video and see if you can determine it. Well, hopefully you added up the charges and you said that 2/3 plus another 2/3 minus 1/3 is equal to a charge of plus 1. And then you thought of a very common baryon that has a charge of plus 1. And of course, your answer was the proton. What common baryon do you think this combination of 3 quarks would be? Pause the video, answer the question, come back for the answer. So this one's going to have to be a neutron because the charges add up to 0. 2/3 minus 1/3 minus 1/3 equals 0. I said earlier that nobody's actually seen an isolated quark. Nobody's ever observed a quark. Well, there should be some physical reason as to why you can't get an isolated quark. And the name of that reason is called quark confinement. And it's based on this idea. If you got, say, a meson with a quark and an antiquark, and you try to separate the two, the bond between them actually gets stronger. It's not like the electric force. The electric force gets weaker. So you pull apart and the bond gets stronger. So effectively that bond is storing more and more energy. And eventually there's enough energy stored in that bond to form a new meson pair. And that's what happens. You stretch apart the quarks, you put in all that energy, and you end up with a pair of mesons rather than a pair of quarks. So we can say that the bond energy becomes large enough to form a new meson. So there were 6 types of quarks and they occurred in pairs. There's also 6 types of leptons and they occur in pairs. So we've mentioned the electron. There's also a electron neutrino. And they're being represented here by fleas because neutrinos, of course, have nearly no mass and no charge. So they, for the most part, don't interact. So we can think of them as being extraordinarily tiny. There's also a tau lepton. It's considerably more massive than an electron, and it also has a pair. There'd be a tau neutrino. And of course, as a neutrino, it would have no charge and nearly no mass. And there's a third type of lepton called the muon lepton. Once again, it's quite a bit more massive than an electron, and it's paired with a neutrino. So there's a tau neutrino. Now the muon and the tau, they're kind of too big, and that makes them unstable. So they won't last very long before they decay into other types of particles that are more stable. Now, all of the quarks and all of the leptons have antiparticles. So I said that sometimes you consider there to be 12 quarks. Well, that's because every quark has an antiquark. So that would make 6 times 2 equals 12. So there's anti-muons and anti-bottom quarks, etc. You can even have a antiproton, which would be composed of 2 anti-up quarks and an anti-down quark. A positron here is really an anti-electron. Now, what are the properties of an antiparticle compared to a particle? Well, antiparticles always have the same mass, but they've always got the opposite charges. And I'm using the word charges there correctly in the plural. One type of charge that we're familiar with is the electric charge. So the electric charge in an antiparticle would be the opposite. Positron has a positive charge, and electron has a negative charge. But as it turns out, there's other types of charge. There's something called a color charge, and it would have to be opposite in the antiparticle. And we'll talk a little bit more about color charge, especially in the next video on exchange particles. And what's really critical about these antiparticles is that when a particle and its antiparticle interact with each other, such as the electron and the proton here, they annihilate each other. In other words, the electron and the proton, they both have mass. And all of that mass will be converted into pure energy in the form of electromagnetic radiation after this interaction. And the amount of energy produced would be given by E equals mc squared, where m would be the combined mass of the two particles. So a little bit of mass here will give you a whole lot of energy. And because a little bit of mass can be converted into a whole lot of energy, antimatter has played a really important role in science fiction. So in fact, the engine on the Star Trek Enterprise was an antimatter engine. And in the movie Angels and Demons, they had an antimatter bomb. So some antimatter had been collected from a large particle collider. And of course they had to keep it separate from the regular matter by using very strong magnetic fields. So if the battery died out in our bomb here and the magnetic field couldn't be supplied, then that bomb would go off. And that became an important component of the movie Angels and Demons. So sure, in a science fiction setting, we can imagine big sources of antimatter. But in fact, antimatter is very, very hard to come by. Our universe is regular matter, and you might be asking yourselves, why is it regular matter and not antimatter? Well, it just so turns out that in the early universe, shortly after the Big Bang, there was really a balance between matter and antimatter. So the matter and antimatter would continually be interacting and changing into photons, electromagnetic radiation, and then the photons would collide together and create particles. There'd be a back and forth exchange. Now it turns out there was some sort of dissymmetry along the way, and regular matter kind of won out over antimatter. So we now live in a matter universe rather than an antimatter universe, and our hydrogen atom consists of a proton with an electron around it. If we'd lived in an antimatter universe, hydrogen would be an antiproton with a positron circling it. So let's summarize the big ideas from the video. There were, first of all, 6 quarks, 6 types of quarks, and they occurred in pairs. So there'd be an up and a down pair, a strange and a charm, and a bottom and a top. There were also 6 leptons. They also occurred in pairs. So there would be, say, a tau particle and its paired neutrino, the tau neutrino. We said that every particle has an antiparticle. And that antiparticle is going to have the same mass, but opposite charges. So when I say opposite charges, I'm including the electric charge, but it turns out there's some other types of charge, such as the color charge. We also said that when a particle and its antiparticle interact, you get annihilation. The mass is annihilated and mass becomes pure energy or electromagnetic radiation. And finally, we said that there was no isolated quarks. That was due to something called quark confinement. And that was basically this idea that as you try to stretch the quarks apart, you're putting all this energy into the bond. And that energy gets converted into mass as a new pair of quarks is formed. And that's all for today, folks. Thank you very much.